Okay, so let's call this rotation of axes and second degree polynomial equations. And I think this is a really important section because it kind of pulls together a lot of things that you learned in algebra and sort of shows you that there was a bigger picture going on all the time. So let's just start by saying what do we mean by a second degree polynomial equation? Well, I know you know what that means in one variable, but I am talking about two variables now. So what I'm thinking of is something that could have an x squared term, something that could have a y squared term, something that could have an x term, something that could have a y term, there could be a constant term. Okay, what else could there be in this missing spot here if this is a second degree equation? What's the one type of term I left out there? Second degree could have second degree or anything less. Well, I've got the two possible first degree terms. I've got the only possible 0 degree term. I've got second degree in y. I've got second degree in x. What's the one other kind of term I could have here if I am allowed as much as degree 2? It's not one that we're used to thinking a lot about when we talk about degree 2. What's the one that's missing?
XY?
Yeah. That would be considered a degree 2 term. And so what we're talking about when we talk about a general second degree equation is something like that. And of course, if you start covering things up, that is, if you put your thumb over different terms, then of course you can make all kinds of conclusions. If b is equal to 0 and that xy term is not there, then of course we've just got the x squared and the y squared and the x and the y and the constant. And of course I know that could be a circle, that could be an ellipse. If a was positive and b was negative, that would probably be a hyperbola. If a was 0 and b was not 0, that would be some kind of parabola. Okay, so actually, if you think about this equation, when you go through all the different variations here of possibilities, and by the way, if it is going to be quadratic, you do have to have at least one of these two terms. If you eliminated both of those, now you're just linear, and that's really not a quadratic anymore. So if you look at all the different variations where at least a or b is not 0, at least one of those is non-zero, these are definitely going to be all the conic sections. And the what they would call degenerate conic sections. Okay, what do they mean by degenerate conic sections? When we were taking that plane, when we used that plane to intersect those two naps, those two cones, the double cones, we said that sometimes you could intersect parts of that system of cones and not get a true conic. Like, for example, when you intersected with a flat plane right at the point where the two cones met, you just got a point. And that's not really a conic. That's a degenerate conic. Actually, do you notice a point is just like a circle or an ellipse that's been collapsed just to the center? Okay, so when I say degenerate conics, I mean things that you can get from this equation that are not really ellipses, hyperbolas, parabolas, or circles, if you want to consider a circle a special case of an ellipse. Okay, but long story short, this guy right here, this general quadratic equation without the xy term, is basically what we talked about in section 1. This is how you get all the conics and all the leftover things that don't really give you a true conic. By the way, what is the list of degenerate things that you can get from this equation that are not conics? Well, obviously you can get a point. We know that. Do you remember that you could also get a pair of intersecting lines? Everybody remember that one? That's when the plane was vertical and cut through the two cones, right in the middle of the two cones, and that made a pair of intersecting lines. You can also get one line, and you should notice that if a and b were both 0 right here, then dx plus ey plus f equals 0 is just the equation of a line. I'll let you think about how you can get that with the plane intersecting the two cones. If you play with that visual, you should be able to see how to get the one line. You can also get the empty set, that is no solution, and you can also get two parallel lines. Now I'll just say these last two, the empty set and the two parallel lines, you can't actually get those by intersecting those cones with a plane. So when I say these are all the possibilities we can get, I am definitely saying those are the things we can get from this equation, but only the point and the pair of intersecting lines can be physically obtained by slicing those cones with a plane. These last two cannot really be physically obtained that way, but they are possible solutions to this equation. Alright, now, that's all great, but the real question is, what happens when that xy term is there? That's what this section is about. We already know all of these. The question is, how do I deal with this guy? Okay, so, let's notice the following. Theorem. If xy represents a point P with respect to a given set of axes, and let's call it x bar, y bar represents a point P with respect to a different set of axes, x bar and y bar, then if, let's see, do I want to say it that way? Then if the, let's call it new representation, is obtained by rotating about the origin counterclockwise through an angle of alpha, then, and this is the part you want to write down, 1, x is equal to x bar cosine alpha minus y bar sine alpha. Y is equal to x bar sine alpha plus y bar cosine alpha. And by the way, I'm sorry, that first one right there take that bar off. That's supposed to be just x. So it should be x equals and y equals. Number 2 is where I want the x bar. X bar is equal to x cosine alpha plus y sine alpha, and y bar is equal to minus x sine alpha plus y cosine alpha. Okay, first of all, let's explain what I mean by representing a point with respect to a given set of axes, just so you have a picture to think about for this. So let's say this is my point P right here. Okay, do you agree that when I say that point P is represented by coordinates x, y with respect to these axes, what that really means is you start at this origin and you go right by the amount x and you go up by the amount y, and that's how you locate that point. So far, so good. But what would happen if I rotated this axis system? So instead of having the x-axis be horizontal and the y-axis be vertical, I take this same perpendicular system and I rotate it around the origin, that is, use the origin as a pivot, and rotate this whole system counterclockwise through an angle of alpha. Well, that would mean, for example, that your new x-axis, which I would not call the x-axis anymore because it's not the x-axis anymore, it's a new axis system. And of course, if I've rotated through an angle of alpha to do that, that means I've rotated the entire system through that angle. That means that axis that was the y-axis has also rotated through that same angle. So far, so good. Do you see that relative to this new axis system, and let me label this guy as y bar up here, do you see that in this new axis system, or relative to this new axis system, that this point P has different coordinates than it did before? Because how do you move from this origin out to that point P now? You move out to that spot right there, and then you move, well, I won't say up anymore, I'll say you move parallel to the y bar axis. Alright, this move that I made right here, that's x bar. This move that I made parallel to the y bar axis, that's y bar. And now I'm saying that P would be represented by new coordinates relative to this new system. Okay, so what's the real big picture here? When you're in your normal graphing system, where you have this perpendicular pair of axes where one of them is perfectly horizontal and the other is vertical, when you say the coordinates of a point are 2, 3, you do mean travel 2 units in the direction of one of the axes, and then 3 units perpendicular to that, which is in the direction of the other axis. If you are moving around in 2 space following another pair of axes that are not necessarily flat and vertical, your coordinates are going to be different to get you to that same point. So it's pretty clear from this picture that this x bar is in no way the same as this x down here. And this y bar is in no way the same as the y, which is this guy here. Everybody with me on the idea of the rotation and that I would have different coordinates? Alright, now I will say this. What I'm saying in these 2 equations above, let's actually start with the second pair. Number 2 here tells you what the coordinates of this original point will be in terms of the original coordinates, because notice these equations on the right sides involve x and y and alpha, meaning that pair of equations in number 2 lets you express the coordinates in the new coordinate system in terms of the coordinates in the old system along with the angle that you rotated through. Okay, what do these two do? They go backwards. They say if I knew the coordinates in the new system and I knew what angle I had rotated through to get to that new system, these are the ones that would take you back to the original xy coordinates in our normal system. Everybody with me there on what they're doing, not necessarily where they're coming from or where we came up with those at all, but how these two sets of equations would take me from one system to the other. Does everybody see that? Now, by the way, this is a specific example, or a particular example, of something more general we'll talk about in Calc 3. This idea of changing coordinate systems. We are doing it in a very specific way here, and the specific way I'm thinking about is rotation. We are doing a rotation to make this change. Alright, now, in what I'm going to do here on the next page, make sure you're looking at these formulas. They're in the book, or you could have them written down. Mainly, I just want you to be able to refer to them and also catch me if I write something down wrong. What I have in the purple box right now is correct, but you know of my tendency to miscopy things and write down the wrong symbol. So make sure you've got those. And I'm going to skip a lot of detail here, but I'm going to talk you through a little bit of where this came from real quickly. Okay, so in our regular XY system, if that's my point P, which means of course this is X and this is Y, well, if I said this was R and I said this was theta, then of course you know sine of theta is y over r, and you know cosine of theta is x over r. So of course, more importantly, that tells you that x equals r cosine theta and y equals r sine theta. And by the way, that right there is super important for the rest of the chapter, and it's something you already know from basic trig, but it's worth pointing out explicitly that I can get the x and y coordinates of a point just by knowing the distance of that point from the origin and the angle that that radial line makes with the positive x-axis. Alright, so I've got those equations that get me x and y in terms of r and theta. So far, so good? Alright, now, when I rotate this point, so let's say I've rotated this point, so now P has moved up here. And how much did I rotate? Well, if we're rotating everything in this system through an angle of alpha, then that means now, isn't this angle alpha? This would be under the new system. So of course, I'm not going to draw the entire picture here, but think about our last picture where I rotated everything in that system. So I'm talking about moving this point and doing a rotation on it as well. Let's say I did that. Can you tell me what the new coordinates of that new point would be? And we're still relative to this normal system that we're in. I'll give you a hint. Actually, let's skip ahead a little bit. I'm going to draw the whole thing right now. I'm trying to break this up into too many little pieces. Let's go ahead and do the entire rotation right now. I was going to try and get you to tell me a little piece of it, but we'll do it this way. Okay, everybody okay there? Where I'm saying, obviously we're saying this is that alpha. That's the rotation of the axes. So far so good. And let's say we have a P. So this is the same picture we had on the previous page. Obviously it's got its own coordinates in the XY system. And we're saying that in that system, if that angle was theta, and this was R, and this was X, and this was Y, then these equations are true. We're saying X equals, and notice when I say theta, I mean this entire angle right here. So far so good. Can you tell me what X bar and Y bar are? And do I have another color for that? Let's do red. Let's do orange. Can you tell me what the coordinates are for this guy? Should still be R, shouldn't it? Should still be cosine, should still be sine, but of what? I see a right triangle there. Yeah, go ahead.
Would it be theta minus alpha?
Definitely. Yep, that's the one we're looking for. Everybody see that? Good. Everybody with me so far? Alright, now, here's where I'm going to skip a bunch of detail, but I'll just say there's nothing profound in the detail you're missing. It's just a bunch of gruesome, nasty, tedious algebra. But what could I do at this point? I could take those last two equations that we just came up with, and I'll just say, you know, could I write X bar as X equals R times cosine of theta cosine of alpha? Does anybody know what I'm doing there? How am I getting that to be? What am I using there to do that, I guess is what I'm trying to ask. How am I getting from that to this? And you don't need to tell me the detail, just what am I using to do that?
An identity?
Yes. Okay, what's your identity for cosine of A plus B? It's cosine A cosine B minus sine A sine B. But in this case, what do you have? You have cosine of theta plus a negative alpha. So that should be cosine of theta cosine of negative alpha minus sine of theta sine of negative alpha. What do I know about cosine? It's an even function, which means cosine of negative alpha is the same thing as cosine of alpha, which means that becomes a plus. What do I know about the sine function? It's an odd function, meaning the sine of negative alpha is the same as the negative sine of alpha, which would get rid of the negative in here, and it would change that negative on the outside to a plus. And that's where I'm coming up with this. So again, more detail there than we maybe need, but I am drawing this strictly from trig identities, the identity for the sum and difference inside a cosine. You obviously have a similar function for sine or similar identity for sine, and that one would give you that y bar is r times sine theta cosine alpha minus cosine theta sine alpha. And obviously I'm copying this down. I did all this on my paper, but I'm not doing it all out in Scratch again. And he doesn't do all this in your book. I'm sort of sketching out the... He doesn't even do this much, and he certainly doesn't do all the detail stuff. Okay, now, look at those, and look at what we had back here. Do you notice that the two I'm getting look like they might be these two, but not quite? Okay, but what do you know about, and this part is important, what do you know about r cosine theta? What is that? That's x. And what do you know about r sine theta? That's y. So do you see that in that first equation you could write x bar as r cosine theta times cosine alpha, and that would be x times cosine alpha. When you distribute the r with this part, you're going to get an r sine theta. That's a y. You can do the same thing with the other one. There's obviously a y right there. And then what's this one? There's an r cosine there, which is x, but there's a minus. So that should be minus x sine alpha. And if you look at those equations, you should notice that's what I have right here in yellow. Alright, so it's not too hard to figure out where those came from. Now, I am really going to skip the next part. I'll just say, I'll just sketch out the first part of the first one. Do you see what would happen if you multiplied the first equation, that is in these two equations, if you multiplied the first equation by cosine alpha, the other side would become what? X cosine squared alpha plus y sine alpha cosine alpha. And if I multiply the second equation by sine alpha, that first term on the second side would be y cosine alpha sine alpha minus x sine squared alpha. So far so good? Do you see what would happen if you subtracted the first equation, or the second equation from the first equation? On the left side you would have x bar cosine alpha minus y bar sine alpha equals, okay, what would happen over on the right side when you take the bottom equation away from the top equation? These two are going to subtract out, and you're going to get this guy minus this guy. But that means when you subtract, this subtraction right here is going to change to an add, which means you're going to have x cosine squared alpha plus x sine squared alpha. This is just x, isn't it? If you factor out the x, there's a sine squared plus cosine squared, which is 1. which means I have x equals x bar cosine alpha minus y bar sine alpha. And if you notice, that's this equation. So this is a little backwards. The equations you get first are these ones where you've made the change of axis, you've done the rotation, and then you can get back to these first two by solving these two as a system. If you just multiply the first equation and the second equation by a certain trig function. Similarly, I can get the equation for y up here by multiplying both of these by a certain trig function. Okay, long story short, that gets us to these two pairs of equations, these two formulas. That's where they come from. Now, the next part's the more important part. So, new page. Let's see, I'm going to skip a little bit of this. So let's consider ax squared plus bxy plus cy squared, etc., etc. So a generic quadratic equation, let's say where b is not 0, because really what I'm trying to do is figure out what that b is doing. So let's assume we actually have a b there. And let's also assume that this is really a quadratic, which means at least one of these two quadratic terms here is non-zero coefficient. So either a is not 0 or b is not 0. At least one of them is not 0. So that we've got an actual quadratic equation for real. Although we would certainly have one even with the b term there, with the xy term. Alright, let's rotate this through an angle of alpha. And of course what I mean by that is we're talking about what the graph of this equation would look like if I rotated the entire graph around the origin, that is, pivoting it around the origin. So obviously, you know, let me give you a real simple example. If I take this guy right here, which you remember from college algebra is just y equals 1 over x. In fact, we've used it in this class quite a lot. Or to put it another way, that's xy equals 1. Do you see that's xy minus 1 equals 0? Okay, do you see that that means the b right there is 1, and the constant term is minus 1. And actually in this example there are no other terms, not even any of the quadratic or the x and y terms. Okay, so actually I'm going to get rid of that because that's not necessary. It's a weaker condition than what we need. The only one we absolutely must have is this. So in this example, this is a hyperbola, isn't it? Y equals 1 over x is a hyperbola. At least it looks like the thing we're calling a hyperbola. Except where is the focal axis for that hyperbola? It's y equals x. Okay, so do you agree that if I rotated that thing 45 degrees counterclockwise to create this, that would be a more standard hyperbola that I'm used to? It's either vertical or horizontal. Actually, in this case, it would be what? Y squared over 1 minus x squared over 1 equals 1. It would be y squared minus x squared equals 1. Okay, which is a real simple formula. But obviously, it's quite a different formula when it's rotated so that the main axis is not the x-axis or the y-axis. So here's the thing. I know this one's a hyperbola, but for a more complicated equation, I might not be able to recognize it's a conic if it's a conic. But if I can rotate it in just the right way, where it turns it into a conic that's in some sort of standard position, then I can figure out what the conic is. I just had to rotate it to see the formula in a nice way. Alright, what we're going to do is figure out how to rotate it, and the big question is, what is the correct angle? and there is an exact correct angle that you need to rotate to figure out what this conic is when it's rotated into a more standard position. Alright, let's work through that real quickly. I'm not going to write all the detail out here. Suffice it to say, if we use these equations, that is, I'm going to a new page now. If we use the equations we had on the previous page, which was x equals x bar cosine alpha minus y bar sine alpha, and y equals x bar sine alpha plus y bar cosine alpha. This is the part you would not like to have to do generically with A, B, C, D's. You're going to do this a couple times in your homework with numbers. But do you agree if I have ax squared plus bxy plus blah blah blah, and I know you're not going to like the look of this, you do agree that I can substitute this and this in place of x and y in this equation? And I'm not going to write all that out. Suffice it to say, the first term would look like what? It would look like a times x bar cosine alpha minus y bar sine alpha squared, which means there's a big FOIL to do there. Notice what the next term would look like. It would be b times x times, and I didn't even leave myself in room, y, which is x bar sine alpha plus y bar cosine alpha, plus, and then the rest, c times this guy squared plus d times this guy plus e times this guy plus f equals 0. Okay, everybody with me on that? And that would still be an equation, but it would now be expressed in terms of this new rotated axis system. Okay, now, obviously there's a lot of algebra to do there, and the one thing that the book does for you, which saves some time, is it says if you do all the algebra, that is, if you clean all of this up, you are going to end up with something x bar squared, something x bar y bar, something y bar squared, something x bar, something y bar, and then some constant equals 0. In other words, when you clean this guy up, you can rewrite it as another general quadratic with new coefficients, where your variables are now x bar and y bar instead of x and y. Okay, where, and I'll write these down, but these are in the book, where a bar is given by a cosine squared alpha plus b sine alpha cosine alpha plus c sine squared alpha. And of course, where would that be coming from? When you do all of your algebra, there will be something sitting in front of all of the x bar squared terms. If you combine all those x bar squared terms, the net coefficient will be this thing you're looking at when you do all of the algebra. And there will be a similar one for b and a similar one for c. The one for b is negative 2a sine alpha cosine alpha plus b cosine squared alpha minus sine squared alpha plus 2c sine alpha cosine alpha. And before I write the c, let's make a little comment here. Do you notice anything nice in this part? I'll give you a little hint here. What's 2 sine alpha cosine alpha? That's another identity. Remember what that is? We've used that a few times before.
Sine 2 alpha.
Yep. So let's go ahead and say that that is minus a sine 2 alpha, if I just rewrite that part. Anybody remember what cosine squared alpha minus sine squared alpha is? That's another one. It would be really nice if it was 2 alpha. And it is. That's another identity. So that means you'd have plus b cosine 2 alpha. And then what's this last one? It's another one of those sine of 2 something. It's plus c sine of 2 alpha. Or to put it another way, I guess we could group the first term and the last term and say we have c minus a sine of 2 alpha plus b cosine of 2 alpha. Okay, now let me write the other ones down for you. And the important one for us to expand into this nicer way was this b bar one. So I'll just write down the other ones. C bar is a sine squared alpha minus b sine alpha cosine alpha plus c cosine squared alpha. The others aren't important in the development we're going to do, but they are needed when you go to actually do the problem, so I'll just write them down. D bar is just d cosine alpha plus e sine alpha. E bar is minus d sine alpha plus e cosine alpha. And f bar is just f. The constant term doesn't actually change, which makes sense. Alright, put all that together and keep in mind what we have for these three right here. And so if you're, now you don't have to be scrambling to write all this down because those formulas are in the book. So I'm going to go ahead and erase those last three because I don't really need those right now for what I'm going to do. Okay, question. What am I trying to do? What's the big thing I'm after? I'm trying to take this equation and turn it into something that's more recognizable as a conic. And the recognizable equations for conics do not have xy terms, correct? It's this guy right here that is the problem. In my new rotated version, then, it's this guy that's the problem. And I see I've gone over here and kept you guys, so let's stop right there, and we'll finish this tomorrow, and it'll only take about 20 minutes from where we are now. In fact, I'll leave this page right where it is, and we will start up right there. But before I let you go, does everybody see what I would like B0 to be? What is it I want B0 to be? What would I like it to be?
Just some kind of a constant.
Okay, good. It could be a constant. Yeah, that's true. The constant I would really like, I mean, you're exactly right. The constant I'd really like is 0. Now, it's funny. Nobody's ever said that before about it being a constant. It certainly could be a constant that you put with this constant down here. But if I wanted to keep that constant the same as the original constant, then I would have to make this guy a 0, and that's the one I want. That's the choice I'm going to make. So we will start right there, and actually we're really close to the end now. We can cook up a formula that actually tells us how to pick alpha so that that b bar is 0. And it, you know, again, the general upshot and formulas are in your book. He's just not giving you any of the blow-by-blow about how this is happening. And even with what I'm doing here, I am leaving out a lot of detail. Obviously, getting from here to here, where A bar, B bar, and all those are these guys down here, is a big leap. There's a bunch of algebra to do there, but there's nothing really profound or deep there. It's just algebra stuff. Okay, let's stop there. Sorry I kept you guys so long. Keep working on your 9-1 for now, and when I give you the homework for this tomorrow, I'm only going to give you about 5 problems, because 2 of them are, they're a bit longer like these, except you have formulas for everything. So it's going to be a lot of plug and chug when you finally get to it. The only thing I'll say is, oddly enough, in this book, he leaves out a big piece of how you actually do these problems. So make sure you look at what we're doing tomorrow with the I'll do at least one full example. And part of what you have to do, he doesn't really show in his examples in the book. So I'll go over that tomorrow. And then we should be set for 9-3. Okay guys, sorry I kept